All right, welcome to part one of our lecture video series for Friday, March 3rd, where we go over how to draw loose dot structures for compounds that contain atoms that maybe share more than one bonding pair. In other words, maybe contain a double or even a triple bond. So the rules for drawing loose dot structures, regardless of the number of single, double, or triple bonds in the compound, are the same. So we're going to review the process that we saw on Wednesday when we looked at how to draw the loose dot structure for water. It's just now we're going to add on to that process a couple of additional rules or steps that allow us to account for any kind of complex bonding, meaning double or triple bonds, that might happen. So we're going to review that by looking at the Lewis dot structure for carbon monoxide as an example. And let's jump right in by refreshing our memory on how to determine the Lewis dot structure for a covalent compound. So step one. Step one is always to count the number of total valence electrons in the compound or the molecule. And you can do this a couple of ways. You can look either at the periodic table and identify the number of valence electrons based on the main group number or column number that your element is in on the periodic table. Or you could use your electron configuration, and here I'm going to show both. So carbon, let's look at this electron configuration. So specifically, we want to look at the valence configuration for carbon, which is here. So using noble gas core notation, that is the helium electron configuration, that's 1s2, filling 2s2, 2p1, 2. We see that we have 4 valence electrons contributed from carbon. And if I count its group number, 1, 2, 3, 4, we see that that is correct. Let's do the same for oxygen. So oxygen follows right after carbon, 2 electrons away, so I'm going to use the same noble gas core, which is helium. I've got my 2s2, and then 2p now 4. So if carbon was 2p2, then 2p3, 2p4, puts us at oxygen. And counting those valence electrons, that is 6 valence electrons. And I can also check that against the column number that oxygen is in, 1, 2, 3, 4, 5, 6. Okay, so now I know how many valence electrons each element, each atom contains in my compound. And if I look at my structure, I have 1 carbon and 1 oxygen. So if I were to count the total number of valence electrons, that would be 10. 4 from the carbon and 4 from the oxygen. Okay, step 2 is to draw or place your element symbols symmetrically around the central atom. So this is typically the thing that's written first. Remember, it is never hydrogen. It is most often carbon if there is a carbon-containing compound. In this case, since we are just a diatomic molecule, right, we have a carbon and an oxygen, it doesn't make sense to call one of these things central. So I'm just going to put these next to one another like so. So carbon next to oxygen. Okay, step 3 is to connect your outer atoms to the central atom via a single bond, meaning we're going to draw a single line connecting all of our outer atoms to our central atom. And remember, according to the Lewis model, anytime we have a single bond that is connecting two atoms, that is 2 bonding pairs, or 2 shared electrons. between your compounds. So if I were, between your atoms. So if I were to look at carbon monoxide, CO, I would connect them via a line, and then this is when I need to start doing my tally of how many electrons I have kind of left over in my bonding budget. So I started with 10 electrons, and in creating a single bond, I've used up a bonding pair, or 2 shared electrons. So 2 of those total electrons I've already assigned to be shared with one another, leaving behind now 8 electrons left. So step 4, what do we do with those remaining electrons? Step 4 says to place remaining electrons on terminal atoms first, such that their octets are filled. And if you have to make a choice, always place electrons on your most electronegative, En, electronegative element first. So we're going to fill the octet of the element that is more electronegative. So in carbon monoxide, C, now I've got it singly bound to O. I need to identify which of these elements, carbon or oxygen, is more electronegative, and I'm going to utilize my periodic table to do so. So we notice that oxygen is right up here next to fluorine, which is the most electronegative element on the periodic table. So following our periodic trend, since this is further to the right across the row, we know that oxygen is more electronegative than carbon. So we are going to place our electrons around our oxygen atom. And remember, we have 8 left in our budget. So I've already got 2 on the oxygen. If I were to look just at this oxygen atom, it's got 2 valence electrons due to forming a single bond to carbon already, meaning in order to achieve octet, I have to add 6 electrons. So let's do that. 1, 2, 3, 4, 5, 6. So I have filled up the octet of my more electronegative atom. And let's do a little tally. So I had 8 electrons left from step 3. And I have now used 2, 4, 6 more to fill the octet of oxygen, meaning I have 2 electrons left. Okay, step 5. This says to place any remaining electrons on the central atom, and then we'll see if we meet our octet from there. And if we had anything to check the duet, we would ensure that we check the duet as well. So if I've got carbon monoxide, so far I've got carbon singly bound to oxygen, which has 1, 2, 3, 4, 5, 6, and encountering that single bond, 7, 8. So 2, 4, 6, 8 valence electrons around the oxygen atom. That octet is full. And now I have to take these 2 remaining electrons and place them on my carbon atom. So I'm going to place them 1, 2. So this is where this process leaves me with my Lose-Dot structure for carbon monoxide. Let's do a quick little octet check. So I should have my oxygen's octet met because what I did in step 3 ensured me, step 4, ensured that I would have their octets filled, right? So the most electronegative atom has its octet filled because I just did that. And let's do a total electron count. Make sure we have no more and no less than the 10 original valence electrons. So 2, 4, 6, 8, 9, 10. Okay. And the oxygen had its octet, but let's look at carbon. So oxygen, we do know, is currently stable. It has met the octet rule. But as we've drawn this, carbon has the 2 electrons that it's sharing with oxygen, plus the 2 electrons that we've placed on carbon that were left over from our bonding budget. So if I were to count those up, right, that would be 2, 4. So this does not obey octet. So this Lewis dot structure is unstable because carbon has not yet achieved octet. So how do we remedy this? We've used up all of our electrons, right? We had 10. I've spent the 10. So what can I now do? So step 6. If the central atom does not have a complete octet after the following step, convert a lone pair on one of your terminal atoms to a bonding pair on the central atom. In doing so, you may form a double or even a triple bond depending on what's necessary. So let's look at carbon monoxide. So far I've got this. Now, anytime you are looking at doing this process of converting your lone pairs on your terminal atoms, so for us, this is going to be the thing that had its octet full, into bonding pairs, when you do that conversion, quote unquote, you're not inherently changing the fact that this terminal atom, or the one that had its octet full, is still achieving octet. All we're doing is we are taking something from being a non-bonding pair of electrons and converting it to a bonding pair. So let's take, I don't know, these 2 electrons. Let's go from being lone pairs into bonding pairs. So if I were to do that, I would have carbon with its original single bond to oxygen, which would leave behind these lone pairs on oxygen. I also had my original unpaired electrons on carbon, and now I have formed a double bond between carbon and oxygen, and let's see if that fixed my incomplete octet problem. So oxygen should still have octet. Let's confirm that for ourselves. So we have 2, 4, and now 2 bonding pairs, 6, 8. Octet is met for oxygen. And how about carbon? 2, 4, so those are our bonding pairs in the double bond. 5, 6, this still does not meet octet. So this is still not stable. So let's see if we can't fix this problem by perhaps doing this another time. So what if I were to take this bottom pair and convert that from a non-bonding lone pair on oxygen into a bonding pair with carbon? So what would I have then? Okay, so left on oxygen would remain this single lone pair now. And then on carbon, its remaining unpaired electrons. I had the double bond formed from the first conversion of lone pairs into bonding pairs. And now I have the second bonding pair that is formed on top of my initial single bond, made from this second conversion of lone pairs into a bonding pair. So now let's check our octets. So on oxygen, so I've got 2, 4, 6 bonding pairs shared in my triple bond with carbon. So 2, 4, 6, and then the lone pairs make 8. Again, when we are converting from lone pairs into bonding pairs, we are not changing the octet of our outermost atom. We are just changing what those electrons are doing, whether they're bonding or not. Now let's check our carbon. So we have 2, 4, 6 total shared electrons with the oxygen from our 3 bonding pairs. Our triple bond, 2, 4, 6, 7, 8. So now we have finally achieved our octet for carbon. And a quick note, even though we have done a really good job of obeying Hund's rules here, placing our electrons as far away from one another as possible, right? Kind of in recognition of the fact that we always fill orbitals with single electrons before we double back and spin pair them. By convention, when we draw our Lewis dot structures, we recognize that a paired electron group, lone pair, is more stable than a single electron group. So this would look something like this as our end result. We would have carbon with a lone pair, oxygen with a lone pair, and they would be triply bound together. So this is our Lewis dot structure for carbon monoxide. All right. So in our next lecture video, we'll do this again, a little less structured with a different compound, and we will arrive at something called resonance structures. So I will see you in lecture 2 for Friday, March 3rd.